the previous video, we just stopped at looking at the explain and analyze outputs. We also talked about nested forms of joins and things like that, right? In the previous videos before that. Let's put it all together now. Let's say that now you've got a SQL statement and that gets executed in Spark SQL. How does the SQL engine behind the scenes go about optimizing for what you've actually specified? So let's just take one example of the kind of decision flow chart that it goes through. I want to just caveat this by saying this is just one example. Many such rules exist as to how to go about optimizing for the queries based on the syntax that's used and based on the configuration parameters that you specify. So this particular example, it uses a very standard way in which the Spark table gets read. So you would, when you construct a data frame in Spark SQL, you would potentially read a table from the Hive meta store, in which case you would say spark.table and give it the name of the table, and then use that to store into a data frame, and then that data frame gets further used for variety of different kinds of operations like transformations and actions. In that kind of a setup, in that kind of a flow, the first thing that happens is to check whether that particular table that's being referenced is that a standard table that's there in the catalog in the Hive meta store, in the Spark meta store. If not, then the way it estimates the size of the table is just simply by looking at the size of the file in Hadoop. And for that, it just uses the standard Hadoop APIs. Behind the scenes, this will use the set of APIs which are mapping to the Linux file system APIs and the respective workers. And those like file sizes are just aggregated together to create like a crude approximation of the size in bytes. That's how the estimation is done for this table. But on the other hand, if it's a table that's actually there in the catalog, then which means the Hive meta store or the Spark meta store knows about it, so that's true. In which case, then it checks whether the cost-based optimizer is enabled. So if the CBO is on, then it looks at the analysis whether the table has had a analyze statement executed on it. In fact, even if the CBO is off, the analyze table status is looked at. So that's why I emphasize that the analyze table is something that you want to do. That's one of your best friends, right, in order to get the best performance. And the reason for that is exactly this. So in either case, the analyze table flag is checked. So if the analyze table is done, that command has been executed, then the stats are obtained from it, right? So if the cost-based optimizer is enabled, then the table analysis that's happened successfully would have resulted in pretty detailed stats about the table, which includes the row count, the size in bytes, the respective column profiles, based on the columns on which you have done the analysis, right? So all of that will get picked up. If the cost-based optimizer is not enabled and the analyze table is done, then only the size in bytes is picked up directly from the analysis. If the analyze table is not there, right, basically the analyze table is not run, then there's a default treatment that happens. The default treatment is based on whether the table is like a partition table or not. If it's not a partition table, then the file system API from Hadoop itself is used directly to come up with a crude approximation of the size in bytes. If the table is indeed partitioned, because the number of files can be large in size, by default, right, Spark assumes that the size of the table is the default configuration, which is the default size in bytes, and that's a value which is set as, by default, 8 XB bytes. 8 XB bytes is basically 2 to the power of 60 bytes. That's massive, right? Way bigger than petabytes. So in effect, let's look at the rookie problem, right? What most rookies do a mistake of when they start working on Spark SQL is they don't analyze, right? And they start to work with partition tables because they read it somewhere that partitions create more performance structures. Then, in which case, the optimizer is completely thrown off because it thinks that the table is always large and so large that um, it's the largest value that it knows about, right? Much, much larger than reality. And that's dangerous in certain situations. Rather, I would say dangerous, and I would say you're really losing out a lot of opportunity on ways in which the queries can be done faster and better. The best case scenario is you've not done the rookie mistake of just blindly partitioning, you've actually done the analysis. And the analysis has happened on every partition, or rather the entire table, and also on some of the key columns, because the columns make the column statistics are important for columns that are involved in joins and group bys and shuffles. So those things are available, and you've enabled cost-based optimizer, and you have stored the table structures in a way that Spark manages it, meaning it's part of the Spark meta store, not some external files which are mapped as a table. So when you do work with external files, meaning that data already exists in some kind of a file system, and you want to start working with it in Spark SQL, one of the first things you might want to do, or rather we would encourage you to do, is to create the metastore equivalent of that same table, which means you bring the data in, even though it's externally queryable and it's easy for you to work with it using just spark.read.csv or something like that. But once you do that, create a data frame and then store that data frame as a table, right? That way, this entire left part of the optimization decisioning flowchart can actually get triggered, along with, of course, the ability to analyze the cost-based optimizer and all of that. So I hope this makes it clear that there is immense value in doing the right thing, and doing the right thing often involves that you pay attention to these small things. So when you write your code in Spark SQL, obviously you're going to write functional code to express a certain logic, but pay attention to these simple non-functional items, right? The analysis of the table, partitioning of the table, analysis of columns, enabling certain configuration parameters, etc., so that your code can actually be much faster. Cool. So for optimal execution, I would always encourage you to, let the optimizer do the work for you, right? Don't take on the headache of the how. The point of SQL is actually to be declarative, and to stay declarative, you have to not worry about the how, which means you need to get somebody else to worry about the how, and that somebody else needs to take your information, right, from your head on what the data looks like, etc. So the best way to do that is to always analyze, even at the column level, for critical tables. And in practice, you will see that the OLAP spectrum is such that you're not going to go back and modify the same data again and again. You're going to load it once, and you're going to read it again multiple times. You're not going to go back and edit it. So if that's the case, the moment that load is done for a particular partition, at that time, you just analyze the table, you're done with it. So the hit that you take for analysis is like a small percentage of the total load time. That way, it gets masked as part of the load, as opposed to doing the analysis later on as part of the select statement. So, which means the loading operation now takes maybe 10% longer maximum, and then all the selects that happens afterwards becomes faster. So the trade-off is actually well worth it. So that's the analyze step. Enable CVO, of course. Enable adaptive query execution. So we didn't talk about that earlier, so let's just spend a minute on this. So when you do a multi-join, multi-operation statement, the relational algebra tree can be quite long. There could be many branches, many nested levels. So in that kind of a setup, it's pretty hard to for the planner to get right what should be the type of joint that happens like somewhere at the top of the tree, um, based on estimated cost that bubbles up from the lower levels, right? So remember we spoke about the cost being like a factor of what are the operations involved. So there's an estimate of the size of the table, right? That's what comes from this subtree, but all of that is for one table. Likewise, you would have the same kind of a join, same kind of a logic um, applicable for the other table involved in the join, right? And then finally, when the join happens, there is an estimate of the result of the join as well. So those estimates keep bubbling up until the point that the final answer is there. And based on the estimated cost at a particular level, the planner optimizer will use a certain physical plan, like for instance the choice of the hash join table or nested loops and so on. So it could think that the cost is actually pretty high and the table is large, etc. And therefore it could say that okay, yeah, let me use hash join at a particular level. But then what could happen is as the respective steps get executed, the actual cost is known, obviously, right? Because you know the data set that you're producing, you know the columns you're producing. Then at which point it can go back and reevaluate whether the choice of the physical planner at the next step, on the next step, and the next step has to be adapted to or not. That's what adaptive query execution means. It says the plan itself is subject to change based on the lower levels of the plan that is already executed. So here, in this example, it could actually execute all these different steps for the filtering of the respective tables and the branches and so on. And then the estimates could be vastly overestimating the size of the data for each of those two branches of data sets that come out and need to be joined at the top level. And at that level, whereas in fact it might find that both these tables are small in size. Therefore, the hash join is like an overkill. The nested loops is going to be far simpler and more efficient to actually get the job done. And it could change the plan at that level and say, I'm going to use nested loops now. Right? And that's going to be authoritative, remember, because the lower levels of the plan have already happened. So that adaptive query execution is pretty neat. Obviously, it involves more compute cycles because it keeps evaluating the plan, whether it's right for every step at the lower level that gets done successfully. But that's worth it because OLAP queries are typically larger, more, they have a long runtime anyway. So if the adaptive query execution configuration takes like 2% more in terms of execution time, but in return, it could potentially give you savings of like 50% for one of the steps. Why not? Yeah, so play with it. Definitely enable that and see and make the best use of it. All right. So what are we paying attention to? So finally, when we come down to understanding the various cost elements, you have to go back and use explain again. And when you look at the explain, you start to see whether the cost is actually getting propagated across the levels accurately. So that's one of the things that you have to get yourself tuned to. Remember, the cost is actually some kind of a relative number, right? It's not an absolute number. It's not like some 10 seconds on the clock, right? That's not what the cost is. Cost is relative to the cost involved in reading 1 kilobyte of data from disk, right? That's the way the cost needs to be interpreted. Joins, whether they are getting reordered, whether they are whether the right join type, like broadcast joins, are chosen correctly, and so on and so forth. So that's the kind of reasoning that you have to build up. And the moment you do it, like again and again, for the first few times, you get that intuitive sense of what the optimizer by default chooses, and when does the optimizer choose better paths, and what data does it need for it to choose those better paths. Okay, so if you take an example of one of these items, like how is the cost propagated? So here, the optimized logical plan, like it's still got these two levels. First is like a relation step. The relation step just reads the data from a particular file. In this case, the file format is a Parquet format. It's got 22 MB in size, and it's got about 1.9 million. 1.9 million. No, 190K rows, right? 190K rows, 22 megs. That's the size of the data. But then, because the analysis has happened correctly at the column level, and there is a filter that happens at the column level which says user ID is less than 0, we find that because the user ID minimum itself is 22, the plan itself can say that this filter will result in 0 rows, right? Therefore, the row count is 0, and therefore the size is like 0 constant, like one byte. So this info basically is available at planning time. It doesn't actually need to use adaptive query execution either for this. And why is this available at planning time? Because of the analyze step. Right? So makes it very conducive. Okay. So one of the last items I wanted to spend some time on when discussing SQL in Spark is the concept of UDFs. So, by the way, we are done with the discussion on cost optimization. Once you go through your assignments, you'll actually see you'll have many opportunities to actually use the explain statement and see for yourself, right? How does the planner work? Anyway, coming back to this particular topic, UDFs is something that it's very useful for you to understand because this gives you an added layer of flexibility as you work through your Spark SQL. So SQL, like I said, is declarative, and because it's declarative, it focuses on the what, right? Now the problem with that is the set of all whats that SQL supports actually might not be enough to get to the power that you need to express the operation that you're thinking about, and that flexibility might require you to start doing some procedural programming, right? Go beyond the declarative. In which case, you do have the option to mix up some of the procedural side with the declarative side, and that functionality is what's called as UDFs, or user-defined functions. In short, the user-defined refers to the fact that you are the user, you're defining it for yourself, and functions refers to a procedural way of expressing logic in fundamentally what's a declarative language, which is SQL. So the way the SQL will invoke the procedural logic is by treating it as yet another function, like one of the standard functions that it has, like sum, count, and average, or string length, and things like that. The difference being, in this case, the function is not something that it understands, right? At least for string length, it knows, yeah, okay, it's going to operate at a certain speed. For some, it knows it's operating at a certain speed. Some can be broken down into partial sums and the full sum, like we saw with the plan example earlier. But in this case of UDFs, it doesn't know any of that because it's completely black box. And that's the flip side to it. The optimizer cannot reason about it that easily. There are hints that you can give as part of the UDF definition, but that only takes you to a certain degree. So if you use UDFs, be prepared for the estimations to go awry. Yeah. So how do you use UDF? So you simply, declare UDF as one of the as a special function. It's already defined for you as part of PySpark, and you can use a lambda formulation for specifying the function that you want. You have to also explicitly declare the type that it returns. So in this case, it's an integer type as non-deterministic, and that is your UDF. So in this case, I'm generating random numbers. Therefore, my function name itself is random UDF. So now in your Spark SQL, you could say, Spark.sql random underscore UDF and give it some parameter. You're done, right? That's how you generate or use the UDF. There's actually another way in which UDFs can be used. So the UDF here that's shown here is actually the standard UDF that PySpark supports. Um, this other way in which the UDFs are supported is through a library that's called as Apache Arrow. Um, this allows you to use a pandas style UDF. I'll talk about that in a minute. But what Arrow is, it's a library which allows for data exchange to happen between the JVM, which is the Java Virtual Machine on which Spark typically runs, and Python on the local machines in the executors. So remember, the executor model, Spark SQL, even if you use Spark SQL, the driver program is operating on the master node. It takes the all the data heavy operations and runs it on the worker nodes. In the worker nodes, it runs it within executors. Within executors, it runs it on the Spark JVM by default. And if you mix it up with some PySpark, the PySpark is operating on in a Python process through what's called as I think a Jython interface. So that Python is actually operating on the local machine, and it gets spun up for the duration of the job and gets toned down after that. So because Python is spun up, you could look at that Python instance as a very useful execution arm for doing single machine pandas. And there is a very specific scenario where this could be very useful, but I'll come to that in a minute. So that single machine Python that's running on each of these local machines, you could run pandas within it, and then you could have the data that's there in that Spark executor be transferred to the pandas locally without going through a shuffle or anything else, without coming through the driver. It just comes locally within the executor instance. That's possible through Apache Arrow as a library. So in essence, it vectorizes the operations that you need to perform from the Spark data frame and make it operate on the pandas data frame in the Python process. And then once it's done, you can bring it back into the JVM and make it available as a data frame, and vice versa. So this seamless exchange of data between the local Spark executor and the local Python, that's what the Apache Arrow library enables. There is a very specific scenario, like I mentioned, where it's useful, and there could be other scenarios, of course, but wherever you feel there is more performance benefits from using the Panda style UDFs, the vectorized user-defined functions, you're going to love this, right? So one scenario for that would be, let's say that you have a deep learning model that you've trained over like gazillions of training data, and as a result, the weights of the deep learning model are themselves so large that we're talking about models of the size of half a gigabyte or 1 gigabyte or 10 gigabytes, right? Some of the large language models which are being released to the open source, like from OpenGPT and so on, those are very, very large in terms of weights. So in that kind of a setup, you would find that the model is itself very large, right? Now, in the classic UDF way of executing, what happens is if you let me explain the problem a bit more. I'll come back to that. So you've trained the model now, right? The model is large, which is fine. The model can be stored in a bucket, like an HDFS or an S3 bucket or a GCS bucket, and then you can have each of the different Spark executors bring that model in for the first time, right? So that it can read it in memory and then use it to do scoring, right? Because you want to use the model for scoring, obviously, and the scoring happens as part of a Spark pipeline. So when that happens, the Spark executor needs to read those models. So the models are there in the remote storage, right? So it needs to read that, bring it into memory, reconstruct the model in memory, and then for each data operation that happens, it needs to apply that model and score. In the classic UDF that PySpark implements, you don't have a mechanism of having long-running state. So what this means is, every execution that happens, potentially the entire model is being read again from S3 or from the shared storage. The model is constructed in memory, packaged together, and then the scoring happens for that record. For the next record for which the scoring needs to happen, the same executor potentially will go back and read that entire thing again. So this kind of a repeat process, excuse me, can be extremely expensive, right? So imagine if you have to read like half a gigabyte or 10 gigabytes over the network for every record for which you want to do the score, like every record in your data frame. That's super expensive. To work around that, the vectorization and the use of pandas style UDFs is actually very beneficial, because then what happens is at the point of invocation of the UDF, you could actually segregate it to declaration and the actual invocation. So at the point of declaration itself, when the handoff to the local Python happens, at that time itself, the UDF is constructed by reading from over the network that big model, and then the model gets constructed in memory, and then it's kept in memory, right? So that when the actual data gets executed, and gets exchanged between the executor and the Python on the machine, for scoring purposes, then the UDF which is already constructed in memory gets applied. So as you can imagine, then the speed at which it gets applied on all of the rows one by one is as though the memory, as though the model was in memory all this while. So once the operation is done, once the scoring is done, then the executor gets cleaned up, right? As part of that, Python gets cleaned up as well. So you're not wasting memory as such, and you're benefiting from reading once and repeatedly using it across multiple rows of data. And this happens in parallel across all the executors in Spark. So that's why the Panda style UDFs are also quite beneficial, especially for data science. And the way you would use the Panda style UDF is just a small way, like difference in terms of the syntax. You would just say pandas underscore UDF, and you would use like the defined version of it, right? Not the lambda expression version of it, but the defined declared version of it. So you can look up the syntax that's there in the Spark documentation as well. Great. So with that, we've come to the end of the SQL portion of this week's lecture. In the next video, we'll look at the NoSQL portion, so that we'll round off our knowledge about everything that's related to big data regarding SQL and SQL. NoSQL, sorry.